Good afternoon, everyone. Welcome to today's webinar on mission engineering within the digital engineering enterprise. I'm Josh. I will be doing some of the logistical stuff and asking you some poll questions at the end of this presentation. This is a live event, so if you are attending it live, over in the GoToWebinar panel, you'll see there's a place to put questions in. So we encourage questions, write them in there, and we'll try to get to as many of them as possible before this event ends. With me today, I have Jeff Baxter, who leads up our engineering group. He's going to help with some of the questions at the end. And the main presenter is Dr. Kevin Flood, our VP of Engineering. And Kevin is going to be going into this presentation. And I think this is the start of a series of multiple presentations that we'll have. Some of them have already been announced, and we're going to have a whole series on digital mission engineering going forward. And we look forward to you guys joining us on those as well. And with that, again, pump in the questions. We'll try to get to them at the end. And Kevin, it's all yours.
Great. Thanks a lot, Josh, and thanks to everybody who joined us. We have a good crowd today, so I definitely ask everybody to join in the question and answer at the end of this discussion. As Josh mentioned, this is going to be the first in a series of webinars that we do on the use of digital mission engineering as it relates to the digital engineering initiatives and the digital enterprise in general. So our objective for today's webinar is to kind of set the stage and the background, discuss a little bit about what we mean regarding digital mission engineering and why we think it's important, some of the important effects that we think it can bring to bear to address some of the critical needs in the industry today, and then use that as a launching pad for future webinars. So with that, why don't we get started? We're going to be using a lot of terminology in our discussions. So we'll begin with a little bit of level setting. In the context of what we're talking about, the notion of a mission is really some important assignment that emphasizes the need for timeliness, some reliance on the quality of the performance of a system in achieving the mission objective, and the reliability of that. So it's wherever these factors overlap with systems and systems of systems. In general, this applies to application areas like national defense, scientific discovery, public safety, search and rescue. But in general, the application of digital mission engineering can apply in more generic ways. So for example, for communications infrastructure or for position, navigation, and timing infrastructure, because those infrastructure elements overlap in these mission areas and are generally evaluated that way, digital mission engineering can be applied to that as well. So with this definition for mission, the engineering part of that then is simply doing the engineering around that. That is planning, analyzing, organizing, and integrating the assets, systems, and capabilities in order to achieve that desired outcome, those desired mission objectives. Digital mission engineering then is really just the application of digital means, specifically modeling and simulation, to execute this engineering function. So one other thing I'd like to highlight by way of background with regard to the definition of digital mission engineering as we use it here is how it overlaps with some of the modeling and simulation activities that go on in the engineering process or in the execution of system operations to execute some of these missions. So what we have depicted here are three really generically encapsulated areas for modeling and simulation. We have modeling and simulation at the mission level, which produces, in the context of digital engineering, a twin that represents the mission environment, the environment that takes into account where the mission systems are executing and some method for calculating the quality of the outcome for those mission executions. Separately from that, we have our engineering modeling and simulation where we're evaluating performance and functionality. So we've got digital twins that are being produced in that domain as well. And lastly, as a general category, we have sort of the logical models, the decision-making representations that we capture in a variety of ways. For the Digital Mission Engineering Initiative, what we're really talking about is bringing all of these three together and evaluating how our engineered systems and systems of systems, as we apply our operational procedures to them, are effective or are not effective at executing our mission outcomes. So in a nutshell, that's what we mean when we're talking about digital mission engineering. An example of that may highlight exactly what we're talking about is this kind of representation. So here you see a theater or global mission, the environment being encapsulated here in this visualization, measures of effectiveness being computed with regard to response times of the systems involved, a capturing of the functionality of the radar systems, the missile threats of the spacecraft in this multi-domain environment, and the logic that's applied with regard to how these systems interoperate in an adversarial and responsive way or in a coordinated way among the response factors. So this is a quick illustration, and we'll actually come back to this illustration a little bit later to talk about how this kind of concept fits into the digital engineering ecosystem, which is an important concept here. So with that as foundation in defining what we mean by digital mission engineering, let's redirect here a little bit and talk about why we think this is important and what you can hope to accomplish through the effective implementation of digital mission engineering. And sort of a capsule summary, this graphic describes what we and many others see happening in the mission application areas that we described previously. And the situation is the following. The missions that we are currently undertaking, the systems that we're utilizing to execute our missions, and the processes that we use to engineer and deliver the systems and capabilities for those missions are becoming much, much more complicated. So the effort and the time required has gone up to deliver those same capabilities. But at the same time, the demand for our responsiveness is being compressed significantly. So the time in which we have to identify the need for our mission objective and the definition around that objective has gotten shorter. And additionally, as a result of that, the time that we have to deliver capability that responds to that mission need has been compressed as well. So really what we're trying to accomplish with the use of digital mission engineering is addressing these two competing requirements. The complexity is increasing dramatically, and at the same time, we have to respond with more capability faster. And we see this in a lot of application areas, certainly in the area of national defense. As we think about the threats that we're facing, threats are responding much more quickly. There are techniques being utilized by our adversaries that are asymmetric in nature. They don't require the same amount of time, the level of technology or complication in order to be effective in deterring some of our areas of strength. The use of cyber techniques is an example of that. And our adversaries quickly adapt to our responses. We actually talked about this a few months ago in a webinar that we did that we called the Space Threat OODA Loop, which essentially discussed the timescale in which our adversaries or threats can be identified and the difficulties that our current systems and techniques have in responding in a timely enough way to offset those threats. And part of the reason we experience these conflicts is because largely our response timelines are gated by the practices that we have in place. Some have described it as industrial age pace for our responsiveness for delivering capability or actually responding with these systems. But these demands aren't limited to national defense alone. Even in the research community for scientific exploration in some of the big science areas, for example, we see that in spite of the growth in the human researcher base, the output, at least measured by publications and new scientific discovery, has actually curtailed or gone down. And at the same time, the funding for many of these projects has gone down. So in the scientific discovery world, there is an impetus not so much to move fast, but to do more with existing or fewer resources and be creative about doing that. And whether we're talking about national defense or scientific discovery, a lot of these lead to making changes that can largely be described by a curve like this influence effectiveness curve. And essentially what we're showing here is sort of a well-known fact for complex programs and initiatives that the ability to influence the outcome is highest at the very beginning before we get far down this process. And as we move forward in time and progress through the development of systems or the execution of missions, we reach a knee in the curve, after which our ability to substantially change those outcomes really drops off dramatically. So if we encounter critical issues late in that progress, our ability to respond is significantly limited, and we can only achieve a certain level of effectiveness relative to what we intended initially. So the fundamental challenge that we're faced with, and the real thing that we're trying to address with digital mission engineering, is the following. We want to move that identification of critical issues as far forward in that process as possible so that we can maximize the total effectiveness delivered and deliver that as soon as possible. And the reason why digital mission engineering is so important to that process is because for the kinds of outcomes that we're talking about, everything begins with the mission. The overall objective is to deliver mission effectiveness and achieve those mission outcomes. So the sooner that we can identify those issues related to the mission definition itself, the engineered systems or systems of systems that are involved, or the techniques, tactics, and procedures that we're using to execute those missions, the more effective we can be at delivering the right outcomes and delivering them sooner. One way for us to look at this that kind of, at least in my mind, really brings this point home is to look at the development life cycle for a complex system. So in this graphic, we're representing that cycle kind of going in a clockwise fashion from concept development through systems engineering, design, implementation, all the way through testing, operations, and sustainment. And there are really a number of important activities that go on all throughout this life cycle and a number of artifacts that drive effectiveness, especially as it relates to the ability to deliver the mission outcomes that we want. Several of those artifacts are represented here as the requirements that we're building our systems to, the models that are used to represent and describe the outcomes that we want, and then the physics-based models and simulation that are used to inform our decisions and drive our designs. So this graphic captures what we've discerned as we've interacted with the community, our government customers, our contractor customers, our consulting customers, and largely they all paint the same picture that's represented here. So if you look, say, for example, at the concept development phase, we can see that we have models represented that describe our system, and the physics tools that we use to analyze those models and set our direction don't cover the entire scope of that. And not only that, they're physically disconnected from that process. So while the models change, the simulations may not, and it creates sources of error that can creep into the process. Maybe more critical is to notice the gaps that occur and the direct breaks that happen as you transition from phase to phase. So in the spirit of identifying issues as early in the process as possible, the fact that these gaps and lapses exist really negates the possibility of making that happen at the earliest stage. And additionally, you see that the physics tools that are used are themselves disconnected. One of the areas where this has really kind of come home to us is in the area of aircraft test and evaluation. So about 5 years, we got actively involved in this area. And one of the things that we observed from our customers is they were struggling with these exact issues and coming to us to see if we could collaborate to produce some successful solutions. What they realized is that by the time these complex systems got to the test and evaluation phase, there was no existing persistent mission model. So that mission demand, that mission objective had to be recreated in the test phase to design the tests around. Similarly, the tools that were being used were not well integrated or worked together. And the result of this is that in addition to requiring additional time to rebuild those models, the tools not working together resulted in the inability to pack as much successful testing activity or test points into a given flight as possible. And as the organizations were figuring out what needed to be tested and how to test it, it turned out, after analyzing the results, that tests had to be reflown up to 50% refly rate. So these were some pretty compelling data points that we observed from direct engagement. Now, the good news here is over the last several years, these organizations have made great strides, and we've been happy to participate in that. So we've seen that implementing some of the digital mission engineering activities that we'll describe here really can deliver some substantial, tangible results and do so in a fairly short timeline. So if we go back and revisit our lifecycle model, this is our take on what we think digital mission engineering can deliver and how it applies across the lifecycle. So first of all, unlike the broken line model that we saw as it exists frequently today, one of the requirements is that the mission model that is established needs to be maintained in some way as a persistent model throughout the entire life cycle, so that traceability back to those mission outcomes at every step in the engineering process and throughout the life cycle can be maintained. Additionally, there are a variety of models, and these can be descriptive models or calculation analytical models that are developed at different phases. And one of the things that we want to do is, in order to identify those critical issues as soon as possible, we want to bring as much fidelity in that modeling and simulation process as far forward in the process as possible. And that can be by using higher fidelity tools and more engineering techniques earlier in the process, or by utilizing models that already exist for existing systems that will be incorporated into the mission execution. In either way, it's important to bring those levels of fidelity forward and do that sooner in the process. And finally, from a mission perspective, a key ingredient, as we identified in that early graphic, is to have a multi-domain engineering, physics-based mission simulation environment that can integrate all of the various models at the appropriate levels of fidelity so that the calculations can be made as we trade off engineering performance characteristics, the operational techniques, tactics, and procedures, and the mission objectives themselves. So these are some of the key aspects that we think can be addressed through the implementation of digital mission engineering practices within the digital engineering initiative. In trying to quantify what the impacts can be here, it's a very broad swath of applications here and a wide range of outcomes. But in our interactions over the last 5 years or so, we have been able to quantify some of the things that will contribute. So I would say a conservative estimate for the impacts can be tallied up through at least these three particular contributions that the use of digital mission engineering can make. So first of all, what we've experienced and what we've been asked for to help solve is that at an individual systems engineering level, those working on these kinds of programs in general spend 24% of their time rewriting tools when they know other capabilities exist that do the same thing. So that's one easy area that can be addressed right away. Additionally, transitioning from phase to phase in general, we find that 30 to 50% of the models and simulations that are created are duplicates of models or simulations that had been done in prior phases. And finally, as we get to evaluating the measures of mission effectiveness for the mission itself, lack of tool integration at the different levels of fidelity and the different functional pieces results in a delay of 6 times what it could be, because so much work has to be done either manually transferring information or writing scripts to overcome those integrations. So depending on how these different factors contribute, when you look at the mission engineering components of that life cycle, by addressing these issues, you can accelerate the timeline by a factor of 2.5 to 6 or so. And that's really what we're trying to accomplish here. Some examples of that, we discussed one of those in a satellite architecture study that we did toward the end of last year. And this was really done as an internal experiment to evaluate for ourselves how quickly we could accelerate the engineering process. And really, this is just an example of one iteration in an overall trade study where all the factors, the architecture, the functional performance characteristics, and the outcome objectives for the mission are being traded off all at the same time. Now, this particular example is being all done within one modeling and simulation environment, which is SDK, but that doesn't have to be the case. Even using the tools that exist today, we can integrate tools from other commercial providers or tools that exist within any organization that represents unique IP that those organizations bring to the overall mission design and systems engineering process. So here you see that scenario that we discussed earlier, that multi-domain missile defense scenario, and you can see a trade study being executed with regard to the positioning of different assets and capabilities in that scenario. That trade study being driven by an external set of tools and being integrated with an external model for measures of effectiveness that might be unique to a particular organization. These two examples that I just discussed largely apply in the concept development phase. But if you remember, one of the points that we emphasized about the persistence of the mission model is that it's important to achieve acceleration in all phases of the operation. So if we were to fast forward, for example, to test and evaluation, it speaks to this example that was done for a C-range test where the test was looking at tracking and detecting and responding to a particular target. You'll see the target here. The point I want to emphasize about this is that we made the point regarding acceleration and the identification of critical issues sooner in the process, that we need to pull fidelity and higher fidelity into the concept designs, whether it's for early phase design or test design. In this case, what was done is we used a product from Ansys called HFSS to compute the high fidelity radar cross-section for the target under consideration, and also generate the as installed antenna patterns that would actually represent the physical performance of antennas on the ship that you just saw. So through this kind of integration, we're able to introduce that level of fidelity, a full physics level of fidelity, very early in the systems engineering process, whether that's for concept design or test planning. And another element of the integration of the persistent mission thread can apply to those aspects of the engineering process that aren't even system related in general. So here you see a view from the Ansys mechanical suite that is looking at the thermal analysis for the CubeSat. And what you see represented at the bottom are the loading conditions, the thermal loading conditions for the system in general or the subsystems in that environment. And the important point here is that the existence of that persistent mission thread allowed these loading profiles to be computed in SDK and imported directly into Ansys Mechanical. And the reality of these kinds of systems, not CubeSats specifically, but complex missions in general, is that the mission requirements are likely to change while we're in the middle of the engineering process. This connectivity and that persistent mission thread allows us to change our design responses very quickly. And while we're on this graphic, I'd just like to highlight at least one lesson that was really brought home to me as we went through this process. We've been working with Ansys now, who's a new partner for AGI, for only a short amount of time, and we've done integrations between SDK and different physics products from the Ansys suite for high-frequency RF, for mechanical and thermal here, and for aerodynamics and fluids in another case. And in those three instances, one of the amazing things to me is that we undertook each of these. We introduced one engineer at AGI to another engineer at Ansys who had never worked together before, were geographically remote from each other, and were asked to solve a problem jointly using products that we had never integrated before. And the effective time that it took those engineers to accomplish that was measured in the span of hours or a day at the most. And that really represents the kind of acceleration and speed that can be realized when tools are used that are designed from the ground up to operate well in this engineering ecosystem. So one last example that I'd like to use to point out the fact that a lot of these integration techniques exist today in spite of the fact that there's a lot of new technology generation going on. is this example that was actually published by a business partner of AGI's, Phoenix Integration, at their 2018 users conference, and was repeated in a webinar there. So I'd encourage everybody to go to the Phoenix Integration site and check out this webinar for more details. But the point of this graphic is that this exercise was done by an organization looking to do a full-up simulation that incorporated the mission design, the system design, and some engineering design within that. The design concepts were captured in a SysML tool, in this case, NoMagic's Magic Draw tool, that captured the structure of the system and the mission operation constraints. Those were fed into Phoenix Integration's Model Center and MBSE tool so that they could be integrated with SDK and other calculation components. SDK evaluated the mission effectiveness, fed that back into the process, and through that technique, created a closed loop evaluation from mission through system through engineering design using tools that exist today. So in upcoming webinars, we'll certainly be talking about future techniques and technologies that are going to help this process even more. But much of this exists already today among some of the tools out in the industry. All right, so before I wrap up this webinar, I do want to take a moment to talk a little bit about the application of digital mission engineering beyond the digital engineering initiatives. So far we've used the engineering lifecycle to highlight some of the techniques that digital mission engineering can accelerate in that kind of process. But the reality is, throughout the world, as these systems go into operation, many of those life cycles and the products of those systems engineering processes exist and are working in concert with each other. And those organizations and individuals who are responsible for conducting operations or performing operations analysis don't really exist in any one of those circles. Nonetheless, the techniques that we're talking about and the acceleration that can be achieved from digital mission engineering applies to that process as well. So if we illustrate that graphically, what we've talked about thus far is the role of digital mission engineering, specifically in the digital engineering process or the digital engineering enterprise. The same techniques, the use of models and simulation at the mission level, the functional performance level, and the logical models as well, combined together, are also very effective at executing operations and intelligence analysis, whether that's predictive analysis or forensic analysis. And there is an important relationship between the engineering and development process and the operations and analysis, in that the operations and analysis can capture models and represent those items that we need to contend with for adversarial forces or uncharacterized activities, and provide that back into the digital engineering process so our next iteration or our next set of capabilities that we produce take that into account. So there's an important ecosystem here over and above the effectiveness of digital mission engineering that is enabled through the collaboration of the engineering processes along with operations and intelligence analysis. A recent example that we saw that was kind of close to home for us is what we participated in here at AGI after the recent shoot down of a global hawk over international waters near Iran. And here's the video, and you can go to the webinar and see this for yourself. But essentially, very quickly, only using public source information, Jeff Baxter, who's joined us here for our Q&A, was able to put together models and show very convincingly that this aircraft, while flying over international waters, could have been detected and could have been engaged with those Iranian anti-aircraft systems as it was actually carried out. So an important and timely example of how these digital mission engineering techniques can be applied to operational analysis. So that concludes pretty much everything that we've wanted to say as far as setting the stage for digital mission engineering. The bottom line here is that what we believe the role for digital mission engineering is for engineering design, digital engineering in general, or operations and analysis, is that it enables the ability to make critical decisions or identify critical issues earlier in the process and leads to a substantial acceleration for the delivery of capabilities or operational decisions. And in the coming weeks, we'll address more detailed components of this. At the end of this month, we'll be discussing how to connect engineering and mission analysis across the life cycle using some of the techniques that we discussed in an overview fashion today with SDK and Phoenix Integration's Model Center. And then in August, we'll be continuing that theme, talking about how to use MBSE tools like Cameo to build physics-infused models that can then be integrated with mission environments like SDK. And then finally, we'll talk about how to pull full physics, high-fidelity models into that mission analysis and looking at integrations with suites of products from our business partner, Ansys.
All right. Thank you for everybody who answered that poll question. And I don't know if you can tell on the line, but I think what was more impressive for me watching Kevin give this presentation is he only took one breath the whole time. And I think he went right through it. It was scary and impressive at the same time. So anyway, on to the questions. The first question that we got is the feature of Ansys and AGI unique? Oops, sorry, Jeff, we got to turn your microphone on. There you go.
Yeah, thank you. I'm not sure which feature of Ansys and AGI the question is referring to. We covered a few different topics, the RF side, the structures and thermal. In general, it's I would say no, it's not necessarily unique. As Kevin described, the tools both were engineering tools designed from the ground up to be very flexible, and as a result, we were able to easily integrate them. In both of those examples, we actually used file input output to do that first level integration. So, for example, when we talked about the RF example for the RCS file that was built in HFSS and then imported to SDK through the properties and will rebrowse to that text file. And so the same thing was done for the thermal model as well. So the thing that is not necessarily unique to just these two products is that the ability to interoperate with other products and have that file input-output structure that is well documented and understood. One of the nice things about the partnership with Ansys and AGI that will be unique going forward is building more native integrations. So in those examples, we actually had to write a little bit of scripting to format the data so that AGI and SDK, or excuse me, Ansys and SDK could do that handshake correctly. Going forward, we're going to make that more of a native interface so that you can just browse to their output files directly and vice versa. So hopefully that answers your question. If I missed the mark there, please just chat it back into the questions panel, and I'll do my best to answer that.
All right. Thank you, Jeff. All right, another question here. Let me see if I can read it from this. All right. In that video that you showed, the engineering design video with the CubeSat, how did you get the mission simulation data into Ansys Mechanical? And I think you partially just answered that already.
Yeah, that partially answered it. I guess if I want to go into a little bit more detail, the specific way that we did that was we used one of the modules in SDK called Solus, Spacecraft Object Library in SDK, which provides a detailed spacecraft simulation environment right within the SDK mission environment. And that allows you to get to a high level of fidelity within the spacecraft model itself. So within there's a thermal model that allows you to report out the solar flux and the Earth albedo flux. And so what we did was we ran a simulation in Solus, and for a CubeSat mission in orbit, we looked at the eclipse times and things of that nature, and then we exported a report in CSV format that had time and Earth albedo and solar flux. And then sent that over to the Ansys engineers. They were able to load that right into Ansys Mechanical and to do the detailed thermal FEA analysis. So So that was how that was done in a little bit more detail. But in general, it was that file input-output share. And as a side note, we are going to be going into that in more detail on the Ansys joint webinar coming up. We'll also be going into more detail on the Model Center integration in the next upcoming webinar, and then also talk about Cameo as well. So we will go into more of the how-to questions and answers in those subsequent webinars. This was really the launching point and setting the stage for the subsequent webinars as well.
All right, thanks, Jeff. One other question that I saw is you had mentioned some of the other industries that digital mission engineering is applicable or starting to be applied into. Kevin, do you have any further on that, like other sectors and things that this is also affecting?
So one of the areas that we've been looking at for a variety of reasons is smart cities, autonomous vehicles. And in doing our research, one of the things that we found is if you look at significant urban problems right now, the costs of, I guess what would be categorized as disasters has been going up exponentially. And those are disasters related to infrastructure failures, man-made reasons, terrorist types of issues, or natural disasters. And the movement has been to instrument cities, create smart cities, and use these technologies to improve our performance and reduce cost around those. So if you look at the intersection of those and evaluate things in the context of mission, as we define it, that's one of the areas that we think is really ripe for the application of digital mission engineering as well.
Great. All right, so another question here. As part of the aircraft T&E community, I'm interested in hearing how you are continuing to engage with this community and how this technology will be used to move ahead in digital engineering.
I guess I can start, and Jeff has probably been more active from a hands-on perspective, but historically, the way we've engaged with the T&E community initially was primarily for the post-test analysis. So when we got involved initially, a lot of the post-test analysis for these very complex mission systems required going through very, very large data sets and examining outcomes either in a tabular fashion or in a purely graphical way. And so our first involvement was just making clear what the outcomes were and helping with anomaly resolution. And what we realized was exactly what we identified on the graphic here today, which is that the problems we really needed to address needed to be addressed earlier in the process to bring that forward into the test design and setup.
All right, the next question is about MATLAB, and MATLAB's a great tool. It's out there. A lot of people like to use it. Is there any further integration planned for SDK with MATLAB and Simulink in this regard, or can most of it be handled in the current MATLAB Simulink integration that already exists?
So I don't know, Kevin, if you have any. I guess my initial impression from hearing that is, so currently SDK has a great MATLAB interface, and it's we've got great documentation to get you up to speed on how to do that. It's very powerful. We have a lot of users using that regularly. I'm not familiar with their new tool sets for systems engineering specifically. I would say we do absolutely plan on continuing our support for the MATLAB interface. There is a Simulink interface as well. It's not as direct as through an S-block functionality. It does exist and customers use that as well, but the majority is the MATLAB interface. I'm not familiar with the systems engineering tool sets specifically within MATLAB and Simulink, but in general, we have customers using MATLAB with SDK all the time. I know I've used it extensively, and it's very easy and very powerful. So yes, we can plan on continuing to support the MATLAB interface. I'm less familiar with the Simulink interface and the other systems engineering tools that they have specifically, though.
Yeah, I would say the one area that we're working on where this would apply is in our aircraft modeling. So in our navigation strategies for our aircraft models, we're creating specific plugins where those strategies, which are frequently developed using MATLAB models, can be integrated directly so that the behavioral models that are captured in those navigation strategies can be integrated into SDK so that as the aircraft flies out and responds to different stimuli in SDK, it will do so in a way consistent with those MATLAB models. So that might be one other area that's coming online and is currently under active development.
All right. Can we integrate cost analysis into the simulation?
Yes, we do that fairly frequently. Cost analysis shows up in a variety of different ways, but typically we find that our customers use a spreadsheet of some sort, and that's one of the frequent models that we use to integrate SDK with tools like Model Center. So the cost as an independent variable is a well-known example of a trade study where we're evaluating cost and performance at the same time, and it creates those typical C-shaped curves where we look for that Pareto front. So that's something that we do quite a bit. Additionally, there are a couple of standard pricing tools that I know Model Center integrates with. So in general, that's something that we've at least done internally here quite a bit, and I suspect a number of customers are already doing that.
All right, another question here. How do you take into consideration the great variability in the environment conditions? For example, thermal boundaries on CubeSats would depend on time of the year. Solar cycle attitude and all these parameters have a huge variability degree. So how do you do that? I think that's a softball for you, Jeff.
Yeah, that's kind of core to STK. So STK has those environment models. It has the environment for the sun. It has the orbit information for the spacecraft, the attitude. And so, for example, specifically the CubeSat example that Kevin showed, what we did within STK is, and specifically within Solus, is we reported out the solar flux and Earth albedo flux with respect to each face of the CubeSat. So you're absolutely right. As the attitude of the spacecraft is changing, the different sides of the solar panels will be collecting that power, and you'll have different efficiencies at different angles. So SDK and Solus handle all of those calculations, and then we fed out that information to Ansys mechanical over time for each of those faces. But yeah, all of the other environment factors SDK handles and has handled for quite a while.
Great. Thanks, Jeff. I think we're running out of time, running out of questions here. So if you have any other questions, we'd love to hear from you. Just give us an email at info@agi.com. Or if you're watching this afterwards on YouTube or on our AGI website, just leave us a comment in the comment section to tell us what you want to hear. We'd love to hear from you. Again, behind Kevin, you can see some of the upcoming webinar dates. And there are more things planned. I don't know, as a spoiler to say, there'll probably be a couple more than this as well. They're just not announced yet. So stay tuned, and hope to see you on July 24th. And if you want to catch us on the rerun, check out our YouTube channel. We're posting this and the analysis that Kevin mentioned earlier that Jeff did for the Radiant shoot down of the Global Hawk. It's on our YouTube channel. Subscribe to that. We'll be posting analysis and product demos and tech tips there, and as well as our webinars. So anything else, guys, before we sign off?
I think that's it.
All right. Thanks, everybody. That's it for today. Again, if you have any questions, feel free to send them in, and we'll get to them when we can.
Great. Thanks, everyone.